All right. So today we're going to talk about an important. Huh? There are some vernacular dialects in which they say a important, but boring white guy from Niagara Falls shouldn't be one of them. So I should say an important, not a important. So there's an important concept here called valence shell electron pair repulsion theory. Huh? Well, I think actually you can sort this out. And by the way, obviously we're going to have to get you caught up. Don't panic. All right, we'll get to it. You know what the valence shell is? And you know what electrons are, right? And you know what it means to pair something up. And you've been in class with me for a while, so you must know the feeling of repulsion. What does it mean to be repulsed? Okay, well, that's how we use it in the vernacular, yes. But what does it actually mean to be repulsed? We have another word that shares a root with it, and that can go in the hand-in folder. I'm just going to collect it as is. What's its sort of synonym is to be repelled. What does it mean to be repelled? Not just not attracted. Listen, I got news for you right now. If somebody tells you you're repulsive, they're not telling you that they're not attracted to you. They're telling you that they are unattracted to you, which is different, right? Listen, somebody's like, I'm not attracted to you, it means they don't think about you. If somebody tells you they're repulsed by you, they do think about you. And that is worse, right? That is worse. Where they're not thinking about you, maybe there's hope. Probably there's not hope. You're sunk. You're screwed. That's real life. Get over it. But if they're repulsed by you, well, that's interesting. Just put them both in there. Interesting. Interesting. Do I mark them both? Yes. And then give him the lower of the two marks as punishment?
What are the books together?
I will give him the higher one, obviously. No, but it's like when you buy a car and you have to pay taxes on it. They calculate it based on the price you actually paid or the blue book value of the car, whichever is more, right? Like you can't get out of paying taxes. You pay whichever is the most. So I guess I should give them the highest grade. So listen, electron pairs in the valence shell repel each other. Electron pairs in the valence shell repel each other. Well, that makes sense. What charge do all electrons have? Negative. And what's true about things with equal charges? Like charges. Like charges? No. They repel. Like charges repel. So that's the idea here. So listen. We've learned so far how covalent compounds form bonds by combining s and p orbitals to produce hybrid orbitals. Today we're going to learn about the three-dimensional geometry of covalent compounds. So hybrid orbitals hate each other. That's a little hyperbolic, I suppose. But hybrid orbitals repel each other. S, P, D, and F orbitals have these fixed shapes, right? You know, an S orbital, a P orbital, a D orbital, and an F orbital, right? Those are the basic three-dimensional shapes of them. And you can see within that orbital that there is a degree of separation to them, right? But these shapes are very efficient for holding electrons in lone atoms. They do not, however, describe the shape of molecular compounds. P orbitals are at 90 degrees to each other, but when an atom makes 4 bonds to make a covalent compound, the bond angles are not 90 degrees. This is where normally we build one, but we're going to do that later. So we're going to draw one. This is where I get like the little spheres with styrofoam and the toothpicks, can't find them. So we're just going to draw it. How's that? Basically, if you took a sphere, and put everything at 90 degrees, that is not the most distance between orbitals, right? On the other hand, we said, what is the optimal angle? Does anyone remember? Very good. On the other hand, if you build it at an angle of 109.5, you can actually repeat that angle. And this is where we need like a little bit of three-dimensional geometry here, which I'm so good at representing artistically because I'm very good at art. So if these kind of go like that, then this, stop. Ugh. This one here goes back into the page, and then this one here would come out like towards the view. That looks terrible. Guys, that looks terrible. I'm ashamed. But you kind of get the idea? That kind of fades back there. Imagine a tripod. You know? That's what I'm going to say. Why wouldn't there be? So 109.5 degrees gives optimal separation. And we call this shape what again? A tetrahedron. Sorry? If you think of these two as being flat on the page, I think there's an infinite number of ways to draw this. The way I've drawn it, if you picture these two as being flat on the page, and you picture this one as coming out at you, and that one is receding back into the page, that's the idea. Yep. Viewed from above, these have an angle between them of 120 degrees. But you realize that that's just an optical illusion. They actually, 109.5, because they're going down together like that. Okay. Hybrid orbitals are able to form in such a way that the distance between them is always maximized. This observance is explained with the valence shell electron pair repulsion theory. VSEPR, but VSEPR sounds stupid, so everyone always says VSEPR. And it's called VSEPR theory. Now, it shouldn't be called VSEPR theory because VSEPR clearly does not say VSEPR, right? But, you know, I don't make the rules. I don't make this crap up. Right? So, here's the idea. When hybrid orbitals form, and that could be sp3, sp2, sp, sp3d, sp3d2, etc. We're only going to focus for now on these. They always form to maximize separation between them. So if there's going to be four things, sp3 orbit, sp3 hybrid, then they are going to form in such a way that those four things are as far away from each other as possible. And we already said what shape that is. That's a tetrahedron, right? But keep in mind, there aren't always four things, because what can we introduce? Well, we could make sp2 hybrid orbitals if there were a what? Why do we get sp2 sometimes? What will be present in the structure? A pi bond. And if it were sp, there wouldn't be one pi bond, there would be two. That's going to change the shape, because hybrid orbitals maximize the space between them. If it's sp3, then it has to maximize the space between four things, because sp3 is four different hybrid orbitals. But if it's sp2, now it only has to maximize the space between three things. And if it's sp, now it only has to maximize the space between two things. And you can probably start to picture that in your head. Maximizing the space between two things is really obvious. You put one on this side and you put one on that side. So right off the hop, you can start to picture what these might look like. But we're going to take a look at a note. So let's do so. sp3 hybridization. Recall that, did I actually put fill in the blanks in here? Oh my God, that's pathetic. I feel so lame. But let's do it together, shall we? Recall that sp3 hybrid orbitals form when 1s and 3p orbitals are combined to create four new hybrid orbitals. These three orbitals are not... Oh, I remember I left this in here because I thought it was funny. This was like my first year teaching, and I was like a real fill-in-the-blanks note guy. And yeah, they sucked. Like, I literally put a blank, and you know what went in the blank? The word not. This is not excellent teaching, too. This is But this is the best my 26-year-old self could do, dummy. They're not 90 degrees away from each other, but 109.5 degrees, which is the greatest possible angle between four spokes. This is called a tetrahedron. We've already said this anyway. Legacy. This is the legacy version. Okay. So the s orbital and 3 p orbitals come together to form 4 new orbitals called sp3 hybrids. And if you do the math, they work out to be at 109.5 degrees from each other. See how much better this looks? Like that one's going back, this one's kind of coming forward. Can you see that? That's the idea. Okay. So now, one thing to note. Anything that's sp3 hybridized is going to have what shape then? A tetrahedron. Except, and unfortunately, I think I broke my tetrahedron. I 3D printed a tetrahedron a couple of years ago. And I think last year, or 2 years ago, I threw it at Preston shopping. Threw it pretty hard. Anyway, so I don't know that I have one right now. But the one thing, see, I should have 3D printed models. Maybe today's project, get my 3D printer going and print one. The one thing you have to note is this. This assumes that maybe this is a carbon, and that's a hydrogen, that's a hydrogen, that's a hydrogen, that's a hydrogen, right? Like methane. In which case, methane would have the shape of a tetrahedron, right? But if you look at the example we just made, chlorate, look here. In the example we just made, that's a chlorine. This is an oxygen, right? This is an oxygen. This is an oxygen. What's the fourth thing on chlorine? The lone pair. This is a lone pair of electrons, which means the molecule doesn't extend to have another atom up here. This is there, but it's not extending out into making the molecule bigger. Does that make sense? Like this then leads to a whole second atom. So it's big and bulky, right? But this is just a couple of electrons. That may from time to time jump up here, but there's not a whole other atom here to then be a part of. Does that make sense? Which means, for all intents and purposes, if there's a lone pair of electrons, this thing looks, shut up, like that, which isn't a tetrahedron anymore. What would that be? Well, it looks like a much simpler shape, just like it's three-dimensional. It looks like a pyramid, doesn't it? You see that? It's just a triangular-based pyramid. Yeah. We'll talk about that in a minute. Basically, not quite exactly. We'll talk about it in a minute. What if it was that would be an oxygen, right? That would be a hydrogen. That would be a hydrogen. And in here, we would just have 2 electrons, right? And up here, we would just have 2 electrons. Is that comfortable? Still sp3 hybridization, right? Oxygen, hydrogen, hydrogen. Complete the octet. We count our electrons. We have 8 of them. Awesome. But that means that if you're looking at this as a molecule, there's no extra atoms here. Just stop. No extra atoms here. That's going to totally make that disappear now, and I'm going to scream. And then there's no extra atom here. What shape is that? Sorry? It's just kind of a little V shape. It's actually not even three-dimensional anymore, is it? That would sit flat down on a piece of paper, right? And we have a highly scientific term for that. Do you know what we call it? We say it's bent. Highly scientific. Bent. Yeah. And then, what if we had, what if we had HCl? What if this was hydrogen chloride gas? Which, we want to keep away from that. That's pretty deadly stuff. But HCl is just this, which means we would say, okay, that's chlorine, that's a hydrogen, and then all the rest of these are just electrons, right? Which means this can be sp3 hybridized, and it could just, for God's sakes, it could just look like that. And what's that look like? Just a line. Does that make sense? So an sp3 hybrid can actually take 4 different shapes, depending on whether it's making 4 bonds and has no lone pairs, or has 3 3 bonds and 1 lone pair, or if it has 2 bonds and 2 lone pairs, or if it has 1 bond and 3 lone pairs. I almost gave you guys the middle finger there unthinkingly, but I course corrected just in time. It was going to be a big one if it has one, but that wasn't on purpose. Anyway, does that make sense? Does it actually? I struggle with this stuff. Like I said, I'm bad at thinking in 3 dimensions. Right? It doesn't come easily to me. So this doesn't come easily to you either. We are compatriots. We are paisan in the language of my people. We're pals. We're in it together. So sp3 hybrid orbitals can actually take 4 different shapes. Any central atom that is sp3 will have one of 4 shapes. Depending on how many lone pairs. Because do you get how a lone pair doesn't make the molecule bigger because there's no atom there? Does that make sense? Like a lone pair of electrons are tiny. So it's not like, it's not like that makes the molecule bulky. It's when you throw another atom in that location by making a bond that the molecule gets bigger. So what are the 4 shapes? Well, we look at them down below, and we say, if there's 4 bonds, bless you, and no lone pairs, then everything's filled in, and it makes this shape, and we say that that is what shape again, this magic 109.5 in all directions? We say it's tetrahedral, or it's a tetrahedron, but more often we use the adjectival form, and we say it's tetrahedral. But if you have a lone pair, now it's not making 4 bonds at 109.5. Now it's making 3 bonds. And the result is that you get something that is pyramidal. In other words, it's a pyramid. And you can see that, right? This does not look like a pyramid, because pyramids don't have big antennas sticking out the top of them. This does look like a pyramid, right? It's got a triangular base, and it sticks up to 1 point. Right? It's a pyramid. That's the worst pyramid anyone's ever drawn. We're going to erase it and never speak of it again. Which? Pyramid? That's a D. Sorry, I'll try to be neater. And again, the reason it's pyramidal is because these electrons don't really take up much space. Not nearly as much space as a second atom would. So functionally, that now just looks like a pyramid. Sometimes you'll have 2 lone pairs of electrons, in which case 2 of those spokes are nothing. They haven't bothered drawing the electrons here, but there'd be a pair of electrons here and a pair of electrons back there. But regardless, what shape is this? Highly scientific. Yes, it's bent. And every year I'm like, surely I just call it that, but that's not what we like the proper term. And I look it up, and every year I'm like, oh, it turns out it is the proper term. Sheben. And then finally, there could be 3 lone pairs of electrons. And if there's 3 lone pairs of electrons, it's only making 1 bond. And if it's only making 1 bond, it has to be a straight line. So that may sound like a lot of shapes to remember, but if you remember the tetrahedron and then just imagine getting rid of spokes, you can picture the other 3. Does that make sense? And again, speaking as somebody who scored in the 7th percentile on a perceptual ability test once, I can assure you, 7th percentile. Do you know how percentiles work? It tells you what percentage of people on a test you beat. So I did a test once of all different sorts of skill sets. I did okay throughout. The perceptual ability test, ability to think in 3 dimensions, 7th percentile. And I watched during a different portion of the test somebody get badly hurt and start bleeding and had to leave. So I know I beat that guy. But do you see what I'm saying here? I do not have good spatial reasoning skills. But even I can figure this out if you spend a bit of time kind of working through it. I will 3D print that model because it's actually really helpful to kind of hold in your hands and kind of picture like, okay, if this were electrons and this were electrons, what's the shape? So I'll try to reprint that for you. How's that feel? Okay? Do you get the idea how if there's 4 spokes at 109.5, if you cover one of them, now there's only 3 spokes at 109.5. basically. That's going to be a pyramid. If you cover 2 of those, now it's only 2 things at basically 109.5, which is bent. And then if you cover 3 of them, now you just have a line between things. The rest of the angles don't matter. Now, you will note that these angles change a little bit. And the reason they change a bit is, note, lone pairs of electrons are a little bit more repulsive than bonding electrons because they spend more time around the atom. So they take up a bit more extra space, which means all the other angles get, if the angle around the lone pair gets bigger, then all the other angles are going to get a little bit smaller. So lone pairs are more repulsive and reduce the other bond angles slightly. You do not need to know the exact numbers. And even I don't know how you calculate it. I don't know if you do calculate it or if it's just been observed experimentally. Does that make sense? It's got to be calculable, right? Like these things live in a quantum universe, but I don't know how you calculate it. I always just see it in the textbook. This is the number. But some scientists sat down and figured it out, right? But does that make sense? Lone pairs, because those electrons don't go as far away to another atom, they just stay around your atom, they're a bit more negative functionally than the ones that have to go all the way around another atom, which means they're more repulsive. And if you're more repulsive, things get away from you. And if things are getting away from you because you're repulsive, I'm speaking about myself here, then that means they're getting closer to each other. So the other bond angles get a little bit smaller. How's that feel? Can we go on to SP2? Is that okay? All right, we'll try. Again, you don't have to be great at this today. We're introducing it. We're going to take some time with it. We're going to practice. Okay. Now, in SP2, it is SP2, not SP3, because we're making a double bond. We're making a pi bond somewhere, right? Which means we can no longer be connected to 4 things. At most, we can be connected to 3 things. What's the furthest apart you can get 3 things? And mathematically, it turns out the best case there is actually to put them flat on a plane and put them at 120 degrees to each other. Because that means that the closest they are to anything else is 120 degrees. And if you take the other angles in other directions, they're all a lot bigger than that. And that turns out to be mathematically the best you can do. So it's actually interesting. When you get to SP, and there's a great thing here because it's easy to remember. When you get to SP2, the molecules actually become, wait for it, this is so great, 2-dimensional. The SP3 molecules can be 3-dimensional. But the SP2 molecules are always 2-dimensional. Isn't that a good way to remember that? That's called a mnemonic device. So if you look here, when it comes to SP2 hybridization, the best arrangement is to sit flat. Now, one thing they haven't drawn here, but I'm going to draw, one of these must be what kind of bond? One of them has to be a double bond. In SP2, there is one and only one double bond. If there were 2 double bonds, it wouldn't be SP2, it would be SP. Good. Does that make sense? So if you look at a central atom and it's only making 1 double bond, it is in SP2 hybridization. All right? So now, if it's in SP2 hybridization, the optimal arrangement is to sit flat. The optimal arrangement for 3 orbitals is at 120 degrees on a flat plane. And there's nothing you can do if you were to do this and sit there with toothpicks and try to get it better than that. That is the maximum distance between things. There's no way to make them further apart than that. So that's the arrangement. Now, how do we say it makes a triangle, an equilateral triangle, and it sits flat? What might we call that arrangement? We call it trigonal, because what shape does it make? a triangle, and it sits flat, so we say trigonal planar. Trigonal planar. It's a trigonal planar arrangement. Trigonal forms a triangle. Planar sits flat on a plane. Does that feel logical? Now, like we said before, what if this was a lone pair of electrons? Well, that would mean that functionally it would look like it wasn't there, right? And now what arrangement would that look like? We've seen this one before. Should bend. There you go. So if there's a lone pair of electrons, it will no longer be trigonal planar. It will just be bent. And
Logan Holmes, please return to class.
if that's a lone pair of electrons and that's a lone pair of electrons, now it will be just a line, just linear. All right. How's that feel? Okay? Sorry? Yes. So now, same effect. Lone pairs of yeah. Because lone pairs of electrons are more repulsive, right? Because they spend all their time around just that atom. They don't have to spend some time around the other atom as well because they're not being shared, which means that they push things a little further away. So when you have a lone pair of electron, the angles around that lone pair will get a little bigger. And if those angles are getting a little bigger, then the angles between everything else are going to get just a little bit smaller. Just a little bit. So you'll typically see that if there's a lone pair of electrons, the bond angles will be a little bit smaller than in a perfect case with all three things. By the way, if these three things are different, sometimes you'll get one of these angles being a little bigger and two of them being a little smaller. For example, a chlorine will be more repulsive than a nitrogen will. So if there's a chlorine on one of these, that will end up tending to make a slightly bigger angle, and the others will make slightly smaller ones. Does that kind of make sense? But you don't have to worry about that. I just want you to be aware of it. I would never ask you to predict. The question will always be the angle should be about. And the answer with any of these is the angle should be about 120. You should know that if it's perfect symmetrical sp2, then it will be 120. And if you start putting other things in, it might change slightly. But it's going to be a roughly 120. Just like sp3 will be roughly 109.5. Now again, what's our mnemonic thing to remember? sp3, those angles can be three-dimensional. They exist in 3 dimensions. sp2, they exist in 2 dimensions. Well, following that to its logical conclusion, sp1 should be, which actually makes sense, because in sp1, there's not 1 pi bond, there's 2 pi bonds, right? Which means we need to keep 2 of the p orbitals, which means, if you come and look here, these would both have to be double bonds, or this could be a triple bond, right? Either or. So, sp hybrids either have 2 double bonds or a triple bond. Does that make sense? I'm going to show it here as a triple bond only because then that leaves me free to say, what if this didn't exist, right? But if you actually look, it doesn't matter. What is the optimal way to separate 2 things? Just put them on opposite sides of each other. Stay away from each other, you. So, this bond angle will typically be 180 degrees. And so, if you think about it, no matter what you do, it's going to be what? Linear, one-dimensional. sp3 molecules are linear. Carbon dioxide's an sp3 molecule, and it is linear, right? This is why, you don't have to draw this, oxygen to 2 hydrogens, water, always gets drawn like this. Carbon dioxide always gets drawn like that. You might have never noticed that, but we have started from early on giving a sense of the hybrid state in the drawing, even though we hadn't taught you hybrid states yet, right? Because what this drawing actually is lone pair, and this angle is about 109.5. Would we expect it to be a little bigger or a little smaller than 109.5? Oh, we have two different answers, which can only be handled by you two engaging in a death match. Whoever survives is correct. We said lone pairs push things away, so the bond between other things gets... No. The bond between the lone pairs and things gets bigger, which means the bond things between each other gets smaller. Yep, you're right. And the angle from hydrogen to any of the electrons will be a bit bigger than 109. You have to think three-dimensionally, right? Like, I can't draw it three-dimensionally because it's on a flat page. Do you know what I mean? Like, those would be behind. That would be like the third leg of the tripod, like behind the thing. Does that make sense? So it'd be a little less then. But it'd be basically 109.5. I think on the previous page it says water comes in at like 107 maybe. Don't quote me. I don't know. Go look it up. Because again, lone pairs of electrons are more repulsive. Think of it this way. Ready? Obviously, I'm not. But imagine I came in and I was just gross. I was repulsive. And I went to stand right here. Right? Are you going to get closer to me or further from me? If you all try to get further from me, are you going to end up getting closer to each other or further from each other? Closer. Because in the process of getting away from me, you're going to inevitably end up closer to each other. Did that answer your question? All right. Did using myself as an example of being disgusting make that more clear? Okay. You're like, no, and everyone else is like, yeah, no, I can really picture that. That's good. They say, like, imagining things in the real world really makes sense of things. And I do, in fact, find you repulsive, Orlando. Anyway, let's take a look here. In this case, the hybridization state of carbon, it has 0 lone pairs. How many sigma bonds? 2 sigma bonds. How many pi bonds? So what hybrid state is it? SP, which means this is 180 degrees. It's linear. Carbon dioxide's a linear molecule. That's why it's non-polar, right? It's symmetrical. Now, even though it's non-polar, it can dissolve in water because it actually reacts with the water to form carbonic acid. But generally speaking, you wouldn't expect this to dissolve in polar things. It's a non-polar molecule. We'd go look it up in mole view. Oh, maybe I won't show everyone's grades. That was great. That's another touch of class, Orlando. Right? So we look up water. Water has that signature roughly 109.5. What shape do we call this again? Bent. What hybridization states could this be? If you didn't know the structure, if all you had was the picture, could that be sp3? No? Because if you took a tetrahedron and covered 2 of the spokes, could you get that? So it could be sp3. Could it be sp2? If you took something that was a flat trigonal planar with 3 spokes and covered 1 of them, could you get that? Sure you could. So it could be sp2, right? One of those could be a double bond, right? If one of them was a double bond, if you didn't know, like if all you knew was the shape, not the bond state, could it be sp? No, because sp will always be a straight line, right? If we look at carbon dioxide, linear, right? Linear. Nope, that's not that. See, that is not what I wanted. Whatever. Anyway, do you get the idea? Oh, those are grades again. Great, that's great, Joe. You had another touch of class. Handy little reminder chart here. Handy dandy little reminder chart here. And we have time, I think, to do a question, and then you can do a little bit of practice. You can do these for homework. But why don't we try one? Well, we're not even going to have time to do this now. This will be your homework. I want you to try them. Right? I want you to try them. You might succeed. That'd be great. You might not succeed. You might go, I can't do this. That's okay. I want you to do as much as you can. Maybe all you can do is draw the Lewis structure. Okay, that's a start. Maybe you can do the Lewis structure and get the hybridization state. Even better. Maybe you can do that and get the likely shape, but fight with it a bit. All right? Don't be afraid to try. I'm not talking to you because you just got here, so this probably all sounds a little overwhelming, I would imagine. We'll get you there. Don't worry. And for anyone who joined a little late, I'm sure this is a little overwhelming. Just do your best. All right? You're going to learn by trying. And the first step in succeeding is, ironically, failing. Failing. Failure is an integral part of success.
Good morning, Eagles. On today's cafeteria menu, we have cream of chicken soup for $2, Greek salad for $4, and today's main entree is chicken souvlaki and rice for $7, pizza for $2 a slice, cheese pizza for $3, and remember, Eagles, we always have fries, small being $2.50 and a large being $4. We also have cookies and brownies for $1 each. That's on today's cafeteria menu. Make it a great day, Eagles.
I need to practice. I'm so clumsy. I need to practice other than just going. Actually practice real like. Foot up there.
You should try and learn, what's it called? Weird chicken pizza.
With what?
Might not pronounce it right, guys.
That's okay.
Chicken pizza.
Abba? Band Abba?
Yeah.
I was told to go this year.
Oh yeah.
There are extra tables.
Oh,
Sorry. It's alright. It's alright.
Is this from Alaska?
Yes.
Oh, God. These are so slippery. Mine have like texture to them at home as if they're made of wood. The plastic, but the textured like they're made of wood. Long December.
Oh, that was not what I thought.
Right? Oh, we're missing one. Okay, but you know what? You don't need lesson number 4 today because you're not going to get to lesson 4. So there's videos. You're in the team already, I think. There's videos for each one, which reminds me I should stop recording today's. So you can go through those, work through those.